Hey everybody, so we're going to finish up the handout that we were working on, and we have 3 more questions to look at. So questions 6, 7, and 8. And I want you to notice a key change here to these question styles. So in each of these questions, they're all very similar in the sense that instead of selecting one person or analyzing what one person may do or their results or something like that, we're looking at a sample of people. So a random sample of 40 adults, a random sample of 50, a random sample of 100. And that's different than it was at the beginning, right? Find the probability that an adult female, so one single person. Find the probability that an adult female, one single person. Now we're looking at multiple people at the same time. Another change in question that you're going to notice is the question is going to be find the probability that the mean overhead reach is, in this case, greater than 212 centimeters. Whereas in the original question, it was just greater than 212 because you're looking at a single person. So you're looking at their own one data point. Here, because we're looking at 40 people, we're looking at their average there. So, and this happens in all 3 of the cases here. So something different is happening, even though the questions look pretty similar. When we sample like this over and over again, so we're not just taking a single person, but we're repeating that process, you want to use what's called the Central Limit Theorem. I'm just abbreviating THM for theorem here. So there's a few things that you have to know. So first of all, in order to use this is your sample size does have to be at least 30, which it is in all of these cases, or your population data has to already be normal. And it actually is here as well. If you go back up to the top, we do see that the distances are normally distributed. So here we have both things being satisfied, but you do need at least one of these things to be satisfied. And then when that's the case, what happens is the mean of the sample like this, the sample there, is going to be the same as the original population mean. But the standard deviation, when you, again, repeatedly sample over and over again of all of those means, is going to be the original standard deviation, but divided by the square root of n. So that is going to affect us in these problems here. That's going to affect your z-score and your standard deviations, depending on how you're solving this problem. So let's look at the first one. And I have another sheet of paper to kind of write bigger on this time. So a random sample of 40 adult females is selected. We're going to find the probability that the mean overhead reach of the sample is greater than 212. Now, remember the mean, the original mean of the population is 205.5. So here we have our center at 205.5. And then we're looking at greater than 212. So the mean of all those samples is greater than 212. So 212 is right here, and we're going to the right. Now remember, there's different ways to do this. So if we use the table, we're first going to have to change this to a z-score. So if I use a table, I have to go to a z-score. So I use x minus the mean over the standard deviation. So my x value is 212. My original mean is 205.5. But here it's going to change because my standard deviation is not just a regular standard deviation here. Because we're using central limit theorem, we're actually going to replace that with the standard deviation divided by the root n. And again, that's because we're sampling 40 people, not just one. So we're going to take our original standard deviation, which was given in the problem, and divide that by the square root of 40. And then the rest of it is just using our calculator. So I'm going to start by doing 212 minus 205.5. I hit enter. And then I'm going to go ahead and divide that by 8.6 divided by the square root of 40. Now you do want this entire thing in the denominator, so I am using parentheses on my calculator to make sure I keep that together. If your calculator does not have parentheses, you could do the numerator and denominator separately and then type in the division another time. So that works as well. And here I get a z-score of about 4.78. So again, as I said before, if you can't do the parentheses, the denominator is 8.6 divided by the square root of 40. So I have 1.359, etc. So what I could do is just take the numerator, which was 6.5, And then just use lots of decimals when you're dividing, and you should still get the same answer there. Now, if we go to our table, our z-score is actually going to get maxed out. So if you look at your table here, and I'm trying to find positive 4.78, I do not have that in my table. It's going to get maxed out here. So you can use the 0.9998, or you could even use probably 0.9999 here, because 4.78 is so much larger still. So you're really out far here on the graph. So I'm going to use 0.9999 at this point for that probability. But keep in mind that the area in the table is always to the left side. So if I want the area to the right, this means that this side is 0.9999. So this side must be 1 minus 0.9999. So if I go ahead and subtract those, you get 1e negative 4. So that means to take that decimal point on the 1 and move it 4 spots left. So 1, 2, 3, 4. So I'm going to attach 3 zeros there. So the probability here is 0.0001. So very, very unlikely that this would happen. Now, again, why is this so different? It's because we're not just sampling one person, we're sampling lots of people, 40 people. And the mean is 205.5. So to get one person larger than 212, well, maybe that would happen, right? But to get 40 people whose average overhead reach is greater than 212 would be very unusual, right? Because they'd all have to have very long reaches overall. So this probability is very small here. For the second one, we're going to do something similar, but this time find the probability between 180 and 215. And again, we're taking an entire sample here. We're also looking for the probability of a mean, not an individual value. So if I draw my picture, so I have that 205.5 in the middle. I'm going from 180 to 215. So 180 is, about right here. And then 215 is about right here. And I'm going right in between. Now this looks like a lot more area shaded in, so I'm going to expect a bigger answer here. But I still have to find both of those z values. So here my numbers are different, so I'm going to have to find both z-score. And again, don't forget, because we're using a sample, we're going to have to bring in that extra square root of n. So for the first one, for x equals 180, we would have 180 minus 205.5 divided by 8.6 over the square root of 50 here, because we're doing 50. And then for the second value, the 215, we would be doing 215 minus 205.5 over 8.6 square root of 50. So let's go ahead and figure those out. For the first one, oops, parentheses, 8.6 divided by the square root of 50, I get, now let me try that one again to make sure I'm okay there. All right, so I guess I get z is equal to negative 20.97. And then for this one here, I would do the 215 minus 205.5, divide that by 8.6 divided by the square root of 50. And we have a z-score of about 7.81. So again, these z-scores are really very, very unusual here. So if I'm using my table, again, that upper z-score is really not going to help me that much. I'm going to be using just 0.999 there because I'm way off the chart. And then for the lower one, again, negative 20 is also way off the chart. So if you look at the lowest value I have is 0.002. So I'm probably going to use 0.0001. Again, something very, very small because these are pretty unusual values here. And my probability here, we'll use 0.0001. Now, what we normally do for a problem like this, when you're going in between two values, we are going to subtract. So I'm going to take that 0.9999 and subtract it with 0.0001. And my estimation would be about 0.9998. So not 100%, but very, very close. Again, the average there is 205.5. So if we're taking a sample of 50 people, it would be very, very likely that the average would definitely be between 180 and 215. This is a pretty wide range of values here. So we have a high probability in this case. For the last one, a random sample of 100 females is selected. Find the probability that the mean overhead reach of the sample is less than 205. All right, so my center is 205.5. My cutoff is going to be 205. It's actually very, very close to that mean, right? And we're going less than here. So if I want to use my z-score again, I'm doing 205 minus 205.5. And I'm dividing that by 8.6 over the square root of 100 here. So if I do this out, I get 205 minus 205.5. So you're getting a negative 1/2 there. And then I'm going to divide that by 8.6 divided by the square root of 100. Now the square root of 100 is just 10. So if you want to do some of this in your head, you can. Here I get a much more normal z-score because I'm pretty close to the center there. So it does make sense. So my z-score is about negative 0.58 if I round. And then I can go to my table here. I'm looking for negative 0.5. And then I want the 8, which is the second column in. So the value I'm looking at is 0.2810 there. All right, so if we had a random sample of 100 females and we're looking for the probability that the sample is less than 205, it would be about 28%, 0.28. Remember that the table is always area to the left. So if you're asking the area to the left, you can just use what's here. When you're looking for in between two values, you're subtracting those two probabilities that you get. And when you're looking for the area on the right, you're subtracting the answer you get with 1. So you have to keep those steps in mind as well. Now, of course, you could also use Excel here. So if I wanted to use Excel for this last one, let me show you what that would look like. Oh, there we go. Just going to minimize this. So for Excel here, and this can vary from question to question, we're going to go ahead and start by using norm. Oh, sorry. Oh, there we go. Norm dot distribution. Now, this one also gives area to the left. So keep that in mind. It's very similar to the table. And you can use it with z-scores, but you can also use it with the original values. So here, if I just do question 8, I'm looking for 205 as my original x value. The mean is 205.5. Now, for the standard deviation, you may want to do this on your calculator separately first, because it's not just the 8.6, it's 8.6 divided by the square root of 100. So make sure you make that update because we're using central limit theorem here. So I'm going to put in 0.86 instead, because that is 8.6 divided by the square root of 100. And then I would go ahead and type in the word true. Let me fix that to give that cumulative value. And then I would hit enter. And we get 0.2805-ish, which is very close to what we got in the table. So our table, we had 0.2810. Here we're getting 0.2805. So very, very close. But again, you do get a little bit of discrepancy between the technology and the table. And that's because we have to round our z-scores as well. So you have some rounding going on, multiple rounding when using the table. Whereas your technology, you actually get a more accurate answer because it uses more decimal places. But it's your choice if you like the tech or the table. They're both pretty easy to use here and take about the same amount of time. So I hope that was helpful to show you the difference between a regular problem and one that we would use with the central limit theorem.